Crash dummies are used throughout various industries to test for safety and help engineers evaluate and adapt their designs. Current crash test dummies are not diverse as they do not have adaptability for many body types. These crash dummies also cost a lot of money to manufacture. Our goal is to address accessibility by making the product cost efficient and model as an untouched data group. For us, this would be 5-year-old girls. We aim to measure the acceleration and force upon impact while modeling the biomechanics of the 5-year-old girl during the collision. For some design specifications, the model should be around 20 centimeters tall with the neck roughly 10 centimeters tall and a head diameter of 14.5 centimeters to mimic a 5-year-old girl's head. The mass would be around 2 to 2.4 kilograms and the range of motion should be around 80 degrees backwards and 60 degrees forwards. Ultimately, these design specifications help us ensure the model accurately mimics the movement of a 5-year-old girl to capture accurate data in a low-impact collision. So, how is it being tested? Well, our test rig consists of a water bottle that's approximately 760 grams mounted to a retort stand to produce a pendulum. It will be released at an angle of approximately 60 degrees to simulate a low-impact strike. The idea is that the potential energy from the height and mass will suffice as a low, constant, controlled impact force. So the physics behind our test rig comes down to our instrument's recording method. Our instrument head records a linear acceleration along the x, y, and z axes plus angular acceleration. This gives a full 6-degree freedom of a snapshot of every impact. To interpret those numbers, we express each peak as a multiple of g, which is 9.81 meters per second squared, which instantly tells us how many g forces the head feels. The g is also the same as gravitational acceleration. The impact severity is governed by the pendulum's release height, which in turn depends on the rope length. The suspended mass of 0.76 kilograms starts at a gravitational potential energy of mgh. As the bob swings down, the potential energy converts into kinetic energy, boosting velocity and momentum. And so because we know that the impact force equals the change in momentum divided by the short collision time, a higher release height and therefore larger h produces a proportionally larger force. To keep tests repeatable and yet classroom safe, we fix the geometry at 60 degrees with a 60 centimeter rope, giving us approximately a height of 0.7 meters. We also created a rubric that allows us to assess the quality of each of these designs against some standard when it comes to test dummies. And this would be against some things like Hybrid 3 as well as Thor 5F. The key metrics include performance, which is rated at 40%. This measures how accurate our model is at representing the model, and survivability. Next is manufacturing at 15%, which measures the ease of production in cost and time. Then we have aesthetics, and this is just looking at how good it is to the eyes, if it's pleasing or not. And then lastly, we have probably one of the more important ones, UI and data capture, weighted at 35%. This is looking at the range of meaningful data captured and the ease of use, looking at how easy it is to interpret and how easy it is to use for other applications. Now that we have established the problem, we began brainstorming 3 different designs that could be used to answer this problem. The first design consisted of a watermelon mounted on top of 4 to 8 chopsticks, which offers a cheap but environmentally friendly and easily creatable solution to simulate the head. Our second design consisted of paper mache as the base for the head, and it would be mounted on a metal frame with wires acting as a neck. And lastly, our third design was to use custom 3D printed heads connected to various plastics to represent the head as well as the neck. We'll be also using a Vex-based solution for this third solution. So, let's see, which one do we pick? Well, we've picked design 1, mainly because it was very easy to produce and also had a lot of benefits of it being cheap as well as environmentally friendly. We prototyped design 1 using a watermelon. How it's produced was by taking one watermelon, approximately 3 kilograms, and stabbing 4 chopsticks in to act as a neck. We chose not to introduce any paper because it kind of melted while the leaking juices touched it. And so, as expected, this was extremely cost-effective and extremely easy to be manufactured. But, however, it lacked a little bit in performance as well as data capture. So, let's play a video of our test. Oh,
It's pretty good.
that was pretty good. That was pretty good. As we can tell from this video, it misrepresented the dimensions of a 5-year-old girl. It was 3 kilograms and had uncontrollable dimensions. Furthermore, it was inconsistent with the anatomical realism and was very hard to change. The chopsticks were rigid and held it unevenly and began to push into the watermelon immediately when it was put on the table, making the head extremely unstable. It produced a weird vinegar odor, which made it extremely unpleasing to the user. And thus, it did not meet the expectation for any of the criteria. And not only that, because it failed in the anatomical section, the data was also unusable. And so we decided to go back to the scratching board. Coming back to the drawing board, after prototype 1, failing completely in every other aspect, we decided to re-look at our decision matrix and re-weight some other things, coming up with our final decision matrix weightings. And so at the end, we chose to just do design 3, despite it being harder. Design 3 focused on using FLM printing to produce a PETG head and potentially using a TPU-based solution for the neck. Design 3 allowed for flexibility due to the varying elastic as well as rigidity properties of the plastics. Design 3 also shifted from a micro-based solution to the VEX hardware solution, since the microbit was limited to 3 Gs. For our prototype, we used PETG to produce a head within the desired dimensions, and used a VEX IMU to capture the max Y and Z acceleration values. Compared with Design 1, we can immediately see an improvement in accuracy from the dimensions and durability, as the use of the PETG meant it also did not rapidly degrade like the watermelon. Now, let's look at a test for our prototype. Go. 0.61. As we can see in the video, with the lack of a neck and stable connection to the ground, the head went flying backwards when hit. Now, it measured 2.8 meters per second squared, but in the next trials, we tried to repeat it, and it gave us 0.6, which is clearly not an accurate value. We had to have multiple people hold it down, and having multiple humans hold it down has a safety liability and is also as unreliable with data since humans apply inconsistent force. So in iteration 3, the biggest thing that we noticed was the head tipping over completely and not having a neck that properly mimics the mechanics of a neck and head system. So the PETG neck was too hard and did not allow the neck to bend. So we produced a TPU neck. We chose to make the neck very long and using a bellows design, as it allowed for high lateral strength while allowing the neck to sway. We did some tests with TPU and noticed that if we used a short bellow, there was not enough range for the motion and was not accurate. Similarly, if we just used a simple cylinder, it was too much rigidity, which meant that it did not sway, presenting the same problem with the PETG neck. And so, additionally, we added a Y base to provide support and ensure the head didn't tip over, and updated the code to use CSV, which can be easily converted to a graphical representation. So now let's look at the test, this time for iteration 3.
Okay.
3, 2, 1. We can see the neck did slightly bend, and we did have a slightly nicer data representation. However, the problem with the neck and the head being knocked over completely still persisted, which meant the neck did not fully do its job. This was still not very accurate. The data reflects something similar because we can see a huge spike after it falls onto the ground in the opposite direction. This definitely skews our data, and we need to better secure it to the ground. For iteration 4, we realized that we needed some type of friction to help us attach the head to the ground and not let it slide. We did some further analysis and noticed that the zip ties that we used lifted it off the base of the ground, which reduced the surface area of the Y base and thus friction. So we designed some thick TPU feet, which used the grippy material TPU to help increase friction. Additionally, for iteration 4, we added data for angular acceleration using parametric equations. We realized that the head was pivoting around a point, and angular acceleration made a lot more sense. And so, let's see if this improved the stability and grip on the ground. 1. Alright, so in this video, we can see there was some small improvements, and looking at data, we did see a lot of improvement in the UI, as now there is angular acceleration data, in addition to the translational acceleration. The base clearly had a little bit more grip onto the bottom. However, because of how the feet were designed, it became a pivot point, meaning the model was still not accurate in representing the neck's mechanics, as it was not pivoting in the neck, but pivoting in the base. For iteration 5, we wanted to mainly address the feet. The feet we noticed in the previous design were too thick, which allowed the model to pivot on it. And also the stem, which went into the holes, were too short. So this new model decided to make the feet thicker, as well as increase the length of the pins. Doing a separate analysis on how human muscles react when hit, we realized that a human, after being struck, does not bounce around in simple harmonic motion. So we also decided to add a set of muscles in the back of the head, which helped dampen the simple harmonic motion. It also represented the human trying to correct their head position back to the original by applying additional resistance in the forward direction. This is modeling the trapezius muscles, as we put it in a V shape in the back of the head. When producing the muscle, we made a few iterations using various mesh materials, and we found that this mesh worked the best. Okay, so now let's look at this video to see the improvements. 2, 1. Wow, that video looked quite similar to before. This was very disappointing. It too got knocked over. Looking at the data, we can also see huge spikes in translational acceleration and also huge spikes in angular acceleration. which at least demonstrates that it's accurate from the first hit, but past that is no longer accurate in representing the model. So our main problem overall was still the head getting knocked over. So let's see, can we improve this? For iteration 6, we remembered that when we were testing the muscles to see if it was able to actually bring the head back into position, we had our members hold down the head physically using their hands. And so, using this concept, that we realized that if we wanted to hold down the head and secure it to the table, we need to properly tape it down. And so for iteration 6, we decided to physically tape down the model onto the table. Another thing that we noticed was the neck muscles popping out from the securing structures, especially the screws. In our situation, the screws were just too hard to screw in properly, and so we just left it be and tried to rely on friction. However, this would not do the trick. And so we decided to use elastics as well as zip ties to fully secure the muscles onto the head as well as the base. And so this helped improve the head and neck stability, as well as improve the responsiveness of the neck to the collision. So now let's look at our test. Wow, that was amazing. This looks exactly like how a 5-year-old head would react to an impact at low speeds. We can see that the neck bends back correctly to how a human would bend back. It snaps back to its original position right after and does not undergo a simple harmonic motion, which is a problem that occurred from just using the bellows. The muscles definitely did do its job this time. The base stuck to its ground, which meant that the data performs and represents the situation really well. If we look at the data, we can see the acceleration Z dampening out, which is from the result of adding the back muscles. We can also see the angular acceleration maxing out after the impact and approaching 0, which actually demonstrates how the back muscles would try to bring the head back to its original placements. Overall, we can see that iteration 6 was very successful and met most of our criteria. In terms of performance metrics, it was very accurate to how a 5-year-old girl would react. Moreover, it was very consistent since all the parts were constrained and remained the same after each test. We also were able to see it was extremely durable as it did not fly out the base or break. In terms of UI, we can see that it had multiple points of data. For example, angular acceleration as well as translational data in the Z and Y direction. It was also very aesthetically pleasing. However, the manufacturing complexity did increase with this design. It took a little bit longer to produce and required a little bit more skill. But overall, it was worth it because of the benefits in the other sections. In summary, for iteration 6, by taping down the base, it allowed the muscles as well as the neck bellows to properly do its function and simulate a 5-year-old's bodily mechanics. Iteration 6 was extremely successful and was very accurate, fulfilling most of the criteria. After this, we did a few extra tests because we wanted to see how the model would do under different conditions of forces. We can see that with the higher forces, it resulted in noticeably larger angular accelerations, which seemed to increase in an exponential manner. Overall, this provides significant, meaningful data for further analysis for a 5-year-old girl. Using these higher forces, it also demonstrates that dummy is able to survive in various conditions and forces, which means able to provide a plethora of data. And so, in summary, we produced a 5-year-old crash dummy model using PEG for the head, meeting the dimensions specified. We then used a bellow neck design to simulate the mechanism of a head pivoting. We then used a large Y base with TPU feet to reinforce friction and support. We taped it down to the table to fully secure it. Lastly, we used muscular structure to simulate the muscles bringing the head back into place. Ultimately, by using this design, we were able to effectively model a 5-year-old girl's head during a low collision impact and was able to harvest ZY acceleration as well as angular acceleration data using VEX hardware. It was cheap and an effective solution with minimal amount of steps compared to other industry dummies. It was also generally aesthetically pleasing and did not have any strange odors. For the next steps, we probably want to try to make it cheaper by using non-VEX parts and buying specifically perhaps from Alibaba. We will try to also be fully bolting down, going away from zip ties as well as elastic bands.